say KNN. Have Amol, Pritesh, and Rohit talk about the others.
Okay. So KNN is basically where K denotes the neighbor, how much neighbor we need to find, right? And from that, it actually select the majority of the vote, and then it looks for that. So it actually needs the uh, training data always, I would say.
Yes. So that makes it what kind of a algorithm or what kind of a model? A non-parameterized model.
Non-parameterized model, yes.
Okay. What does a NN stand for?
Nearest neighbor.
Nearest neighbor.
And what we are doing is we need some way of calculating distances. So we use the normal Euclidean distance. So square root of x1 squared plus x2 squared plus x3 squared and so on. Right? So the basic premise for KNN is that in that multidimensional space, if data belongs to the same class, they are likely to be close to each other. That is the basic premise. Okay? Who wants to talk about perceptron?
I can go.
Go ahead.
Yeah, so in perceptron, we need linearly separable data. In 2D, it looks like a line. Like a line will divide the data into two different parts. And in 3D, it would be a plane. In that, we try to find not the most optimized plane, but a plane that separates the two data. It does it basis the so basically the target variables, the target class is divided to plus and minus. It has polarities.
Yep.
And basis that polarities, we just differentiate the points are either the points are on which side of the plane.
Yeah. And what is the overall algorithm? So basically, you start with a random separating hyperplane, and you check every
point.
And if it is misclassified, you update the hyperplane.
Right.
And updating is basically adjusting the parameters so that you're guaranteed that the current point that was misclassified is now classified correctly. And then you repeat it for all points.
Yes.
Right. And there is a theoretical result that says that you're guaranteed, if your data is linearly separable, you're guaranteed to have a separating hyperplane in a limited set of iterations. So it doesn't go on forever. You're guaranteed to find a solution.
Yeah.
Okay. Okay, good. SVM. So remember SVM, we talked about like 4 things that we can specify for SVM. Pritesh, Amol, Shruti.
SVM data is not linearly separable.
Kind of. So we start with linearly separable data. What is the primary, like how do you step up from perceptron to SVM? Like what's the main, let's start with that.
There are a few points that are misclassified from perceptron.
Right, but there's a even more fundamental difference.
Yeah, so we consider the margins
Yes.
of points from the hyperplane, and accordingly we adjust the hyperplane. And if points lies in between the hyperplane from each of the side, we consider the slack variables, and we consider that C value to calculate the slack variables.
Yeah.
So
Yeah.
Yeah. And the
Yeah,
points, yeah.
so we start out by saying that in a perceptron, you can have an infinite number of possible solutions which separate the linearly separable data, right? But we need
Yeah.
some way of saying which one is the best. And the way we define the best is by saying we want we want a hyperplane whose margin is maximized. Right? So
Right.
when we talk about SVM, the first thing to distinguish is it's not just taking any separating hyperplane, it's taking one that maximizes the margin. So that is called a maximal margin classifier. And margin is just the minimum distance of any point to the hyperplane. So we are maximizing the minimum distance of every point from the hyperplane. And the points that are the closest to the hyperplane, what are those called?
Support vectors.
Support vectors, hence the name, right? So the first thing that we say is it is optimizing the hyperplane. Then the next thing is we can actually allow for points to be inside the margin or even misclassified, like both Pritesh and Amol were talking about, by allowing for slack variables in the formulation and how much weight we give um, the um, the minimizing of the margin versus the slack variables is determined by that hyperparameter C, right? So that's the second part. The third part is what Pritesh started out with. What is that?
Data is not linearly separable.
Separable. So then what do we do?
Kernel.
Kernel.
Yes. But what does the kernel do?
It
Does the
it takes the data points to higher dimension
Yes.
and help us to classify them.
Yes. So the idea is the data may not be linearly separable in its current form, but when we project it to a higher dimension, it is linearly separable, right? So that is the third thing. And the fourth thing is the kernel trick, right? And what's the importance of the kernel trick?
it actually mathematically does the calculation behind the scene,
Yeah.
and it does not really use the projected data,
Yeah.
and that actually help us to reduce the processing time.
Exactly. So you get all the benefits of mapping stuff to higher dimensions without the overheads of the calculation.
Right.
Right. So it's like the artificial sweeteners. You get the taste, but you don't get the calories. Right. So that's that. Okay, good. Akshar, we're doing a quick review, and you joined just in time. So we've gone over KNN, perceptron, and SVM. They are all classification algorithms, and we split that into parameterized and non-parameterized algorithms. What is the standard function we use to split the data into the training set and the testing set?
Train test split.
Train test split. If you want to scale the data so they're all in the same range, we can use standard scaler. There are others as well. And then once we instantiate a particular classifier, uh, how do we do the training and the testing and the evaluation? What are the functions called?
So fit transform
Yeah.
on the training set, training data, and then the transform on the test data.
That is the standard scaler. You're absolutely right, but that's the standard scaler. But if you want to just train your data using a particular classifier, like let's say you've used nearest neighbor or perceptron, you just have to instantiate it and call the fit method.
Yeah, right. Fit.
Fit, then how do you run it on the test set? You call the predict method,
Predict.
right? And finally, score will tell you what the accuracy of your model is.
Mm-hmm.
Okay. Um, Examples of hyperparameters.
K in
K,
KNN.
C,
Yeah. C, and also which kernel we use in SVM, right? That's also a hyperparameter.
RBF,
Yes, RBF, which is the other one?
Linear.
linear,
Yeah.
poly.
And
Poly.
so linear is basically the same as what the normal SVM is. Polynomial and RBF are actual kernels. Um, and, and then when you want to evaluate what the value of the hyperparameter is, you can actually take out data from your training set, keep it aside, and then try out different values of the hyperparameter and evaluate on the validation set. Okay? Okay, good. So with that as a warm up, let's get started with what we were doing yesterday. So what I wanted to point out is that if you think about what we did with SVM, right? The focus was not so much. The focus was mainly on saying how. One sec. There we go. The focus was mainly on saying how do we formulate the problem so that we can use some mathematics to solve it. That was what we were trying to get at, and we formulated it, and then we said, oh look, this is a quadratic optimization problem, and there's a black box that will tell us the values that solve this problem. We didn't get into the details of that. What we've done yesterday is along the same lines, right? We said that we have some data, and what we are going to try to
The
do
screen
is,
is still
yeah, hang on. Yeah, okay. We have some data, and what we are going to try to do is just say that can I model this data using a straight line? And we looked at different ways of how we might come up with a reasonable looking straight line. But then we said, okay, hang on a second. How do I quantify whether a line models this data well or not? And we went through a couple of evaluations, and we said, okay, I'm going to define something called the mean squared error, which is literally, as the name says, the error is the difference between the actual and the predicted value, uska square, and we take the mean of that across all the points that we have, right? So that's what we call loss function. We can also use other parameters like the mean of the absolute value of the error, the mean of the squared error is what we are doing. And then we can do root mean square and R squared, right? Now, this up to this point, if you think about it, this is very similar to what we did with SVM, because in SVM, we spent a lot of time saying, okay, how do I calculate the distance? And then I want to minimize the distance, and then I want to come up with a hyperplane that maximizes that minimum distance. So that formulation was very important for us, right? Out here, we've actually come to that point in a very natural way. We've come up with something called a loss function, which is defined the way you see on the screen. And then we are saying, okay, I have this loss function. Now, what do I do with it, right? How do I use this to find out a particular point? Now, what we're going to say is, uh, for this loss function, what do you guys say? Do I want to minimize it or maximize it?
Minimize.
minimize it.
You want to minimize the loss function. You want to minimize the error. So uh, the way we are going to do this is well, we'll see how to do this, but I want you to get an intuitive feel for what it is that we're doing. When I minimize the loss function, I am trying to minimize the distance of each point from the line, but not of each individual point. The sum of these distances is what I want to minimize. So in a sense, we are treating, we're taking into account every point, and we are saying, let me get a line that does the best job across this entire data set, not just for a single point or a few points, right? Okay, how do we minimize a function? So first of all, let's examine this function a little bit more. Let me go all the way to the end. Okay, so I'll write the function once again. Over all points I. Okay, this is actually summation over I. Y actual is, the values that we have. y predicted, this is, in our case, W0 plus W1x, right? So I can write this as minus W0 minus W1 xi is ka square, right? So now I've just written LMSE, but this LMSE is actually a function, right? A function has inputs. What are the inputs out here?
X value and
Yeah.
Y actual value.
Yeah. What else? So if I say that my inputs are, and I've written capital X because it could be multidimensional, X and Y, right? And there are I or N such values. So if I give it a particular X and Y, I can calculate MSE if the parameters are fixed, W0 and W1, right? But now if we stop and, think about this for a second, I can say that, look, okay, hang on a second. If my W0 and W1 is fixed, then I'll calculate my loss and I'm done. And that's what we did yesterday, right? We took y is equal to x and y is equal to 1.2x. And then we did the calculation and that was fine. But what I want to do out here is I want to minimize the value of the loss. What can I vary in order to change the value of MSE or LMSE? It's precisely these guys,
Yeah.
right? So I would say that my loss, I mean, in general, if it's fixed, then it's a function of this. But I'll say this is a function of x, y, and w, right? So w is now a parameter. It's a variable that I can change. And I want to change it in a way such that I can minimize MSE. In fact, what I'm going to write out here is LMSE is a function of w given x and y. So this notation is saying given x and y, I can vary w, right? It's a function of w. So for different values of w, I can calculate the loss. And x and y is kind of fixed. It's from my input data. Does this make sense? Because this is a very important point.
Okay, but then how do we assume the W? Because we don't know the
So
W.
we are going to calculate it. So that's what the procedure is going to be. But the
Okay.
first thing is you've got to appreciate that W is a variable out here. That's
Input
what I
variable.
want guys to. Yeah, sorry, what was that?
Input variable.
I wouldn't. Well, it's an input to the function. Yes.
Okay.
Hmm?
But then normally, let's say if we run the perceptron, right?
Yeah.
Usually when we say okay predict, right, or draw the hyperplane,
Yeah.
we can get the output from there as an W value, right?
Yeah. So
W0.
okay, let's no, that's a very good point. Let's talk about this for a second.
Okay.
I have this loss W, and corresponding to this, right? I have what should I call it? Let me just call it f of x, right? And so this loss is this function, right? F of x is what? W naught plus W1x. So I shouldn't write f of x. I should say f of x given W. Okay. Let's talk about these, and they're kind of two sides of the same coin, but I want to make this very clear, and then we'll go back to what you were saying about the perceptron. It follows the same pattern, right? So I have two functions out here. One is f of x given W. The other is L of W given x and y. What is the meaning of both of them? So f of x given W is saying that, look, suppose I tell you what W is. In the example that we did yesterday, W was y is equal to x. So it's basically, W was just um, 0 and 1, right? So W is given, and if I plug in a different value of x, I can calculate f of x, which is W0 plus W1x, but W is fixed. My variable is x. As x changes, I can see how f of x changes. On the left-hand side, I have a different function. I have a loss function where x and y is fixed. And I'm going to change w. If I change w, the value of the loss function changes. Does that make sense?
Yes.
But
Okay.
how do we fix the x and y?
No, the x and y is from my training data.
Okay.
Right. So for all of those points in my so for all of these points, right? Here's one line. So for these guys, I have some W0 and W1. I can calculate the loss. If I change W0 and W1, I can recalculate the loss. So I'm changing W0 and W1, but these points are remaining the same. And I'm calculating it for these points.
Got it. Yeah. Perfect.
Now let's talk about what happens with perceptron. It's the same thing because in a perceptron, sorry, yeah. Hang on. Okay, let's be consistent. So now think about, this part, when I wrote the loss on one side and the f of x on the other side, you should recognize that on the left-hand side, we are in the training phase where we are changing W and we're trying to figure out the W that minimizes the loss. On the right-hand side, we are on the testing phase. We are saying, given this W and this input, calculate the value of the function. So we can do the same thing when we are talking about perceptron. How? When we look at the perceptron and I say, okay, let me start with some random separating hyperplane, right? What is this random separating hyperplane? This is defined by my W vector. And then for these data points, once I find a point that is misclassified, I'm adjusting the vector in some way. So I am physically changing W. Whoops. I'm changing W in some way, right? But I'm evaluating it over all of these data points till I get something that separates it. You see that? So the data points are constant and my W is changing. I'm updating my W. And then when I go to the testing phase, if I get some new point somewhere and I say, is this class 1 or class 2? At that point, my W is fixed and I'm feeding in that point and I'm asking it, what is the Y? So it's actually the same formulation as what we have right now. Make sense, Rakesh?
Yeah.
Any other questions?
No. Good.
Okay. Anyone else?
How many times we need to set a value for W?
In which situation?
Like we did here, like we have shifted this hyperplane.
So for a perceptron, there is actually a theoretical high upper bound, which says you need to iterate at most so many times in order to get a separating hyperplane. Right? I'm not going to go into that derivation. It's actually very elegant, but there is a theoretical upper bound. For the linear regression, for the example that we are doing now, we are going to do it in one step. It's not going to be iterative for now.
Okay.
Okay. I know it's a bit unsatisfactory, but in fact, I'll share a document that we wrote with. I wrote with a couple of students. So the proof of the perceptron convergence is fairly straightforward. If you just Google it, you'll find it immediately. We were trying to come up with a better way of illustrating how the algorithm works. And also, we came up with what I thought was a much tighter bound than what other people have talked about. But it turns out, of course, somebody else had already come up with it. So, but anyway, I'll share that document with you guys.
Yeah, one more. Let's say if new data points come up and those are noisy data points, I mean, very closer to the hyperplane.
Yeah.
And in both the situation, in perceptron or in the linear regression, in linear regression that we just saw that we can set it only once, right? And in perceptron, we can set it at most their upper bound.
Yeah. Yeah.
So in the linear regression, if the new data points are very noisy, then is there a chance to misclassification of those points?
So, okay, with linear regression, we are not doing classification.
Yeah, we are predicting, right?
We are predicting.
Yeah.
Okay? And I'll show you examples. So, this is where if you have more data points in your training set, then even if you have a few points that are outliers, it's not going to make much of a difference. And you'll see why. Once we do the calculation, you'll see why it won't matter, right? But if you have, so for example, I'm trying to find, um, uh, uh, let's say these are my data points, right? If I have only 3 data points, sure, I mean, I'll come up with some, line that fits it. Maybe this one, right? And then in my testing, if I have a point that's actually out here, right, I'm going to predict this value, but the actual value is out here. So it's going to be really bad, right? But let's keep this purple point and see what happens if, my data set is now expanded to have points that are like this, right? Then all of a sudden, I won't be going with a blue line. I'll be coming up with a line that maybe looks like this, right? And then my error is a lot less. So the point is that the more points you have in your training data, outliers are not going to matter too much, right? In fact, okay, let me say this separately as well. If I have these points, right, and I include in my training set a point out here, okay? So if I have the yellow points, what is it? Oh, 4. Okay. If I have the yellow points, I get the blue line as the model. If I include the red line, guess how much the blue line is going to shift? It's going to be like this.
Extend.
No, it'll just be like this. It'll be like a barely, you can't even make out that difference. Right? So the point is, the more data you have, the more rigid, or not more rigid, the less impact outliers are going to have.
So does this mean, so regression का मतलब यही है, right?
क्या है?
Like, we're gonna shift this line based on the data.
No, hang on.
Yeah.
Regression का मतलब है come up with a function that can predict values, predict the output value for a given input. So let me write this down. So for classification, right, we want to predict which class my input belongs to. For regression, we want to predict a value. Okay. That is the big difference between regression and classification. So regression is not saying ki, oh, if there is a point, then the line shifts by a very little amount. That is a characteristic of the model, and that too of a linear model. Right? And I've kind of hinted at this a couple of times last week also. We are going to study how robust the model is to changes in the input data. So if my input data changes, how much does my model change? We're going to look at that, and that gives you a sense of what is a good model versus not a good model. But we'll get to that.
I have one question.
Yeah, please.
So, if we are saying that we have one independent variable here and we are predicting a value of a
Yes.
dependent variable that's dependent on the independent variable.
Yes. Yes.
Now, let's say if I have two dependent variables,
Hmm.
out of which one has more weight
Hmm.
or more priority over
Hmm.
the second,
Yeah.
where is that accounted in this equation?
Yeah. Okay. So, okay, we are going a little bit ahead of this, but I think it's fine. It's a good discussion point. So right now, I'm saying, I don't know if I should talk about it now. Well, let's talk about it. So right now, what we're doing is something called simple linear regression. We'll later be talking about the general linear regression where you have variables where you have multiple variables. Right now, we have only one independent variable, right? I can actually write this. So this W0 plus W1x, right? If I have two variables, well, okay, let me do this. I can write this as W0 into 1 plus W1 into x. Guess how I can write this? This is basically W transpose x, where x is the column vector 1x. Let me call this x arrow. You see this? So this is W0, W1 dot product with 1x. Okay?
Yes.
Okay. Now, suppose I have two variables. So now I don't have x, but I have x1 and x2. So now, and in the most general case, I can say, okay, so then this is W0 plus, let's say W11 x1 plus W12 x2,
Mhm.
right? And this will basically be W0, W11,
Okay, one,
W12
two.
into
One,
1,
x1, x2.
x1, x2, right? And then maybe if I have a more complex model, I can also say I can have maybe um, uh, W22 x1 x2, right? So actually that's not completely correct, but anyway, the 2 is supposed to represent like this is, it's got squares, so I shouldn't write it as 2. Um, so it would be, let's say, W21 x1 squared plus W22 x2 squared. And then I'll have to come up with some way of encoding x1, x2 as well. I don't know, W222 or something. And these guys would change. The vectors would change, right? Okay. So if I have multiple variables, I can have this. Even with a single variable, I can have W0, W1, W2 into, sorry,
One.
1 x and x squared.
Mhm.
Okay. Okay. So now your question was, suppose one independent variable is more important than the other. In this case, I have x1 and x2. I could also say the same thing applies if the x squared term is more important than the x term. That's possible, right? How will the model capture this? Question to everyone on the call. How will the model capture this impact?
The loss will increase.
The loss, yeah, but how will we find out? So once we've trained the model, what tells us that X1 is more important than X1 has a bigger impact on the output than X2?
Scalar,
Scalar, yes. Which scalar?
kind of what we usually do
Okay.
in the
Hang
in
on. Just
SVM.
look at this. Just look at this equation, right? Y is W0 plus W11 X1 plus W12 X2, right? So if x1 changes by a small amount and y changes by a large amount, right? W11 is going to capture that. It's going to be, so for example, I could have y is equal to 1 plus 10x1 plus 2x2. right? So it is a scalar in the sense that it's multiplying x1, but these coefficients are telling us that if x1 changes by 1, y changes by 10. Whereas if x2 changes by 1, y changes only by 2. So in that sense, x1 is 5 times more important than x2. It has, not important, it has 5 times a bigger impact on the output than x2 does. Does that make sense?
Yes.
Yes.
The same thing holds, for example, if I had y is equal to, let's say, 4 plus 3x1 plus 20 x squared, not x1, right? So this is telling us that the square term has a bigger, it matters more, the output depends more on the squared term than on the linear term. And how can we say that? We look at the w's. That is telling us what the importance of each term is. Got it? So for example, if my data is linear, right, then we've been saying, oh, y is equal to w naught plus w1x, but it's actually plus w2x squared plus w3x cubed and so on. But these guys are all zero implicitly. So this is saying that the x squared term has the output does not depend on the x squared term at all, or the x cubed or higher powers and all of that. Right? So that was a very good question, Rohit. So you see how, so not just independent variables or multiple independent variables, but even if I have a single variable and I have multiple terms, it's the coefficients that tell us what impact it has. And that is what we're trying to discover. The whole point is trying to figure out what is um, the correct value of the W's so that my function models the data, and that quote unquote function models the data is the training that we want to do right now. Okay? Any other questions? Okay. So we come back to we go around the whole world and we come back to the same point. Okay. How do we find these W's? Right? And one thing, again, I'm repeating this, but this is really important. In the training phase, for a given set of points, the X and Y, we want to find the W that minimizes the loss. And then we're going to turn around and in the testing phase, we're going to fix W and we're going to say, given a particular X, calculate the output Y, right? So what we want to do is we want to minimize LMSC. What are the parameters out here? W given X and Y. Right? So this minimize is over all values of W. So one dumb way of doing it is evaluate LMSE for all values of W. Of course, we're going to do a much better job than this. And I want to find the minimum of a function. This ties in beautifully to what we talked about yesterday. How do I find the minimum of a function?
Differentiate and
Differentiate and
equate to 0.
Equate to 0. Now, and this is the reason why I was saying, so thanks, Rohit, that's exactly right. I take the derivative and set it to 0. And to jog your memory, why does that work? Because if I have some function like this, right? The derivative is the slope of the tangent at different points, and it's at the minima and maxima that the derivative is a horizontal line. Horizontal line means slope is equal to 0. So I take the derivative, I set it to 0, and then I solve for W because that is the thing that I'm varying. And that is going to tell me what the value of W is for which my loss is minimized. So do you guys get the high level idea of what we are trying to do out here? High level, just intuition.
Yes.
Okay. So now let's just do it. So I'm going to take, and this is the reason why I was hammering away right at the beginning. You're saying that the loss is a function of W. W is the knob that we are tweaking, is the knob that we are varying in order to get the minimum loss. That is the freedom that we have, where we can change W any way we want to get this. Okay, my W in this case is W naught and W1. Right. So I'm going to introduce a little bit of uh, uh, I don't know what to call it. Like there, not a little bit of terminology out here. Well, not terminology, a little bit of technique out here. So I want to see how my function varies with W naught and W1. So what I'm going to do is I'm going to say, okay, assume my W1 is fixed. Let me see how it varies with respect to W. And then I'll solve for with respect to W naught, and then I'll solve for W naught. And then I'll say keep W naught fixed and let's see how it varies with respect to W1. Okay. Normally, if I'm taking the derivative, I say d by dx. But if I have multiple variables, I shouldn't say x. Let's say I had only one W, I would say d by dw. But now I have two, W naught and W1. So I'm going to say dabba by dabba W naught and dabba by dabba W1. So these are called partial derivatives. I'm just saying this for completion. You don't have to, like memorize any of this or really understand it in too much depth. Basically, we are taking the function and we're saying, I know it's a function of two variables, W naught and W1. But to keep my life simple, I'm going to split it into two. And first, I'm going to say it's a function of W naught and W1 is a constant. And then I'm going to say it's a function of W1 and W naught is a constant. Okay. Okay, so let's just take the derivative. So dabba by dabba W naught of 1 by n summation ya minus W naught minus W1x squared. Okay. And there's going to be a couple of things that I'm going to go over very quickly. Again, you don't need to know this. You need to understand what it is that we're doing, right? The first thing is the derivative of a constant times a function is constant times the derivative of the function, right? So what that means is this 1 by n, I can take outside. Okay, and it's a constant. N is a constant for a given set of inputs. Okay. The second thing is that the derivative of fx plus gx. Okay. D by dx of f of x plus g of x is the derivative of f of x plus the derivative of g of x. Right? Or in other words, the derivative of a sum is the sum of the derivatives, which means that I can actually move this derivative inside the summation. Right? So this is 1 and this is 2. Okay, so what do I get? I get 1 upon n summation d by dx ya minus w naught minus w1 x whole squared. And I just realized this is not x, this is w naught. Okay, now what I do is something called, so first of all, d by dx of x squared is 2x. And finally, d by dx of, or I'll just write chain rule out here. I won't write out the rule because it'll become too complicated. Okay, so what I get is 1 by n summation. If I look at this guy, right? I can say this is kind of like x squared, right? So what is the derivative of the square? It is
2x.
2 times, yeah, ya minus w naught minus w1 into x into, now I take the inner thing and I take its derivative, right? So dabba by dabba w naught of ya minus w naught minus w1x. And this finally, again, the 2 is a constant. I can take it outside the summation. I get ya minus w naught minus w1x. Now, the derivative of ya is a constant. So the derivative of a constant is 0. The derivative of w1x, again, it's a constant, so it's a 0. So I'm just left with taking the derivative of minus w naught, which is just minus 1. Okay, so I'm including all of this just for completion, but don't freak out about this. Just keep one thing in mind. I have a function called the loss function, which is a function of w. So first I'm taking its derivative with respect to w naught, right? And if I apply a few rules of derivative of functions, the derivative of that LMSE ends up with respect to w naught ends up equal to this. And then I'm just going to set this equal to 0. And then I will solve for w naught. Everything okay so far? I know this is a lot of math. Don't worry if you don't follow the steps, right? Keep in mind this, that I had this definition of my loss as a function of w. I took its derivative with respect to w naught, and I got this equation. And I'm just going to set that equal to 0 and solve for w naught. Is that fine?
Yeah.
Okay. And now, now we just have a little bit of algebra. So let's see the summation of these guys, right? So let's see, what can I do? I'm going to kind of ignore the 2 and the -1 because I'm setting it equal to 0. So they just cancel out. I'm not removing the n though, because that's going to be very useful. So what I'll say is this guy is 1 upon n summation of ya minus 1 upon n summation w naught minus 1 upon n summation w1x. Okay. What is the summation of 1 upon n summation of ya?
Mean of.
Exactly. It's just the mean, right? In the last term, I have w1 is a constant. So it doesn't depend. This is over I, right? So it doesn't depend on the I. So I can take it outside the summation and I have 1 upon n summation of x. What is that? Is the mean of all the x's. And finally, for the middle term, right? Again, the w naught I can take outside the summation because it doesn't depend on I. And I'm just summing up 1 n times. So that is n. N cancels and I just have w naught. So this is x bar into w1. Right? So I'll go over it again, but we're getting close to the answer. So I just wanted to write this down. So I get y bar minus w naught minus w1 x bar is equal to 0. And therefore w naught is y bar minus w1 x bar. Now, when we're writing the program, we don't have to do the derivation. The derivation is for you to understand how we get the formula. But you remember I was saying it's going to be like one step. I kind of cheated. It's one step for W naught and one step for W1. So it's two steps. But anyway, so I can calculate W naught because I have all my data. I can calculate the mean of the X's, the mean of the Y's. We'll see what W1 is. I just plug it in and I've got my answer. Does this make sense?
I didn't understand the W naught minus 1 upon n summation I goes from
Yeah,
1 to n and
So let's do this. 1 upon n summation W naught, I going from 1 to n. The I is picking up individual data points, right? From the perspective of those data points, W naught is not changing. When I go from one data point to the other, W naught is constant, right? So I can take
so
it
it is n
outside the
times. Okay,
summation.
okay, got it, got it, got it. N times
W naught
W0.
upon n,
Okay.
yeah, summation I 1. And if I add 1 n times, I get n. So W naught n upon n, W naught. Okay? So
Yeah.
again, don't worry about the details of the math that you've not understood. Keep in mind the main points, which is basically I have the function for the loss and I want to find out how to minimize W naught. So I take the derivative with respect to W naught. I do a bunch of algebra to come up with this equation, right? Which I'm going to set equal to 0 and solve for W naught. And then with a little bit more algebra, I get this final value. Is that fine? Yes, no, maybe?
One confusion I have.
Yes.
It's W naught here is my bias, or it is coming from that vector?
Uh, so what do you mean by bias?
That we see in that equation y is equal to mx plus c.
Yes. So it is that C term, the
C term. Yeah.
y-intercept, right?
Yeah.
So
Yeah.
the reason why I was trying to, probe what you meant by bias, it is what is called a bias. It is the bias term. But don't think about it like that. Just think of it as I've got this equation W naught plus W1x. I want to find the value of W naught that minimizes this.
Mm-hmm.
Focus on that. Okay?
Okay.
Now the challenge out here is it is in terms of W1. So we also need to find the minimum value of W1, right? And we can follow the same steps. And you see out here how I got -1 for the derivative of this guy. If I take the derivative with respect to W1, instead of -1, I'll get -x, right? So what I'll get is, if I take the partial derivative with respect to W1 of the loss, 2 times y minus W naught minus W1x into -x instead of that -1. And now let's see what we can do with this. So um, I can get rid of the -2. But now what can we do? So let's see. So I'm going to do 1 upon n. I think I can get rid of the 1 upon n as well. Okay. So I'll have summation, and I'm going to say y minus y bar. Let me do it step by step. Plus y bar minus W naught minus W1x into x. And then I can split this up. So summation y minus y bar into x plus, okay, now W naught I can replace with y bar minus W1x bar, right? So now what I get is y bar minus y bar plus W1x bar minus W1x into x. Okay, and now we are home free. So this is summation y minus y bar into x plus summation, these guys cancel, and I can take w1 common, and I'll call it x minus x bar into x, and this will be minus w1. And now when I set this equal to 0, I can write w1 is equal to summation of y minus y bar into x divided by summation x minus x bar into x. Okay, again, I went very quickly out there, but let me take a step back. We have the definition of the loss function as a function of w, which is w0 and w1. I take the partial derivative of that function with respect to w0, I'll get this equation. If I take the partial derivative with respect to w1, instead of that -1, I get a negative x, right? And after that is just algebra. I remove the minus, I remove the 2, I remove the 1 upon n. I substitute w0 that I'd calculated before, y bar minus w1 x bar, right? And then after a bit of manipulation, this is just algebra. I get w1 is summation y minus y bar into x divided by x minus x bar into x. Okay. And at a high level, what I want you guys to recognize is this. I started with that loss function and I said, how do I calculate the values of w0 and w1 so that that loss function is minimized? And how did I minimize it? I took the derivative, set it equal to 0, and I solved for w0 and w1. And what I get is this is called a closed form expression. It's a formula. So I know my x and y's. I can calculate the y bar and the x bar. I can plug in the values. I can calculate w1. And I can plug in the values and I can calculate w0. And that's how, in not one step, but 2 steps, I can directly calculate w0 and w1 such that my loss function is minimized over the data that I've been given. Does this make sense?
Yes.
Any questions? Any place where, and like I said, don't worry about the details of the derivatives or even the algebra. The high level picture is something you guys should be able to explain. That I've got data, I'm going to model it as a linear function. The parameters are w0 and w1. So I want the values of w0 and w1 that minimize the loss function. And by taking the derivative of the loss function, setting it equal to 0 and solving for w0 and w1, I get these equations for w1 and w0. That is the key thing to keep in mind out here. Okay. So now, we can just go ahead and implement this. This is just a straightforward equation, right? And what I'm going to do is, this is a sheet that I'd kind of shown you guys when we talked about, let's see, when we talked about, in the open house. So it will be familiar, but today I'm going to go over it in quite a lot of detail. Okay. So what I'm going to do is I'm going to say that I'm going to assume I've used B instead of W in this sheet. It doesn't matter. It's like it's just a term, right? First, I'm going to generate the data set. I'm going to fix a value of B0 and B1 so that I can generate my data, right? So if I generate, let's say 100 values for X and I calculate 3 plus 1.2 times x, right? And then I plot it. I'm going to get something that looks like this. So I've generated 100 values of x. I plug it into this equation, b0 plus b1x, and I get this line. Now, of course, all of these points are exactly on the line. And we're going to be talking about real world data and noise and stuff like that. The data that we get is not exactly this. There's always some noise. So when I calculate y is equal to b0 plus b1x, there's actually going to be some variation around that actual y. And the way I model that is by adding some noise to the calculated value of y, right? So the orange line is the original data. The blue dots are now the noisy data. That's this data plus the noise. Okay. Everyone okay so far?
In real life, what is the noise exactly?
Yeah, I'll talk about it shortly, but basically there could be a number of things. One, it could be measurement error, right? Our the
Standard
tool
errors.
techniques we use to measure it are not absolutely precise. One very interesting source of noise could be maybe there's a second variable that we don't know about,
Mhm.
right? That is possible, which we have not included in the equation, but that causes the actual value to be different from what the exact value is. Right. So in fact, the model that we're going to come across, the model that we're going to develop, model not as in the machine learning model, but the statistical model statistical approach that we're going to say is that there is a lot of uncertainty in what we do, given that we are trying to so there is going to be some part of the error that we can minimize that's captured by the loss function. There is some part that cannot be minimized at all. That is called the irreducible error. So we're actually going to quantify that as a parameter and we're going to treat it mathematically. Okay?
Okay, but so let's say if I have a real world scenario,
Yeah.
there could be multiple things uh, that are outside our data points. That could be
Yes.
noise, right?
Yes.
But
Yes. Yes.
then do we quantify it in one variable?
Yeah.
All
So we just say
the
that's noise. We just model it as noise.
Okay,
Hmm?
okay.
And just think about it, right? So let's take examples of what we've seen. So we have the iris data set, right?
Mhm.
Where the length and width of the petal and sepal are, I don't know what they are in, like in millimeters, for example, right? But it may not be 2 versus 3 millimeters. It might have 2.5 or 2.8 or 2.8875, right? There could be variations between those that are not being captured because of the precision of our measurement, right?
Right.
And if you remember, when we were plotting stuff, we just took two of the columns because we can't visualize four-dimensional space. So the other two columns still have an impact on the data, but we're not using that at all, right? The California housing data set has 13 columns.
Mhm.
But for all you know, the house prices are driven by demand and supply, which is kind of what we're trying to model. But there could be other parameters that have not been captured at all in those 13 parameters. So we're going to
Right.
treat that as noise. Okay.
Okay.
Okay. Are you guys comfortable with a Gaussian distribution? Like when I say random dot normal, do you understand what that means?
Nope.
Okay, we'll cover that when we get to it. Okay, so now this is basically the stuff that we talked about, right? The loss is y actual minus y estimated square. So this is the mean squared error. Y estimated is b0 plus b1x, and I've used k instead of I. So see, the thing is, you should be comfortable with the form of the equation. It shouldn't be like, oh, पण आपण तर y predicted केलं होतं, or we said yi, not yk. Those are just irrelevant details. I mean, it's just, you can, it's a placeholder basically. Okay? And then look at this. My B1 is yn minus the mean of y, right? The whole thing multiplied by x, and that is summed up. And that is divided by x minus x bar into x. That's exactly the formula that I derived in the notebook. Okay? And my B0 is again y bar. So that's np.mean. And then B1 into x bar. And if you remember, the way I generated this data was using 3 and 1.2. And when I do this calculation, I get the values of 3.006 and 1.19. And the only reason why it's not exactly 3 and 1.2 is because of the noise that we added. Right? And in fact, if you see this, right, the blue dots are the original, that's supposed to model the actual line. The red line is the variance. So its slope is slightly less than what it should be. And the intercept is slightly higher. So it's kind of shifted up slightly. But it's pretty damn good. Right? And one of you guys asked this question. You should actually try this out. So take this data set and add one more point where instead of y is equal to b0 plus b1x, make it like 100 times bigger. And then when you run through the whole process, you'll find that if I have 100 points and one point is an outlier, it barely changes this line. There'll be a very little impact on the line. Right? Okay. Now, what I want to do is I want to talk about a little bit more about the loss function, because out here we were able to come up with a closed form expression for W0 and W1 or B0 and B1. But in general, the loss function will have not just X, it'll have X1, X2, X3, X4, and you could have like multi-dimensional, W0, W1, W2. We don't want to sit and calculate the derivatives by hand each time, right? And in general, we shouldn't be doing that. Because this is kind of like a manual thing, right? We derived the formula and implemented it. We want to be able to calculate the values of W0 and W1 or B0 and B1 in a much more automated manner, right? In order to do that, I want to start thinking about exploring what this loss function is. So I'm going to show you how we can visualize this in Python. But before that, a quick check. Any questions on what we've done so far? All good? Okay.
Yeah.
So like you see, I mean, this is like we've just scratched the surface. For simple linear regression, we were able to figure out the formula, plug in the values, get this. But we're going to do a lot more with this optimization, and that's what we are building up towards. Okay? So the first thing I'm going to do is I want to take a step back and talk about how we might visualize this loss function. Okay, and I'm going to switch back to my notebook for that. Okay. And if you think about it, this loss function, I'll write down the formula once again. One upon n summation ya minus w0 minus w1 x whole squared. Okay, so this loss function is a function of two variables, w0 and w1. So if I want to visualize it, right, I would have to create a 3D plot where I have w0 and w1 on the two axes and the loss function on the third axis, right? So it's going to be a three-dimensional plot. And what I'm going to get is some kind of surface, and I want to understand what that surface looks like. So we have a closed form solution. We can calculate the minimum value of L for W0 and W1. But to visualize the surface, I need to calculate the value of L for all values of W0 and W1. right? So I can list out different values of W0 and W1, and I can put in two for loops, right? So for I in the W0 range, and then for J in the W1 range, I can calculate the L, right? And then, so for this and this, maybe I get L out here. Then for this guy, it's out here. For this guy, it's out here. So I might get some kind of surface like this. It's difficult for me to draw it, but you can imagine, right? So for all combinations of W0 and W1, I can pick and choose. I can plot on the Z axis the loss value, and I'll get a three-dimensional surface, right? Or in two dimensions, I can also, like, if I look at it from the top, right? It will look something like this. So I'll have, sorry, right? I have my W0 and W1, and then I can draw contours. I can say that, this, sorry. Hmm. I can say this is a line where L is equal to 1 or 0.1. This is the line where it's 0.2. This is the line where it's 0.3. So it's like looking at a contour map of a hill or a mountain. And essentially the contour lines join all the points at the same altitude, right? So you get a sense of, so if I have lines that are very close by, it means that the mountain is very steep out there. If the lines are further apart, then it's not as steep, right? So do you guys understand these two visualizations that and how we can calculate those?
Yes.
Right? Okay. So these two nested for loops is the dumb way of doing things. Dumb in the sense that, I mean, it's very explicit, but it's also very, very slow, because the whole point of NumPy is to push. We talked about this, right? We talked about it in the context of broadcasting. The whole point of NumPy is to push as much calculation into compiled code as possible, especially loops. So we want to be able to do these calculations without resorting to writing loops in Python, right? So there's two things that we're going to apply out here. And one is something called a mesh grid, and the second is broadcasting as usual. So how does this work? So for mesh grid, what we're going to say is, look, let me generate a list of possible values for W0. So let's say I go from 2.5, 2.6, 2.7, 2.8, 2.9, 3, and then 3.1, 3.2, all the way to 3.5, right? So basically I know the value is 3. So I'm just taking 0.5 below, 0.5 above, and I'm generating all values in between them. And then my W1, I think it was 1.9. So we can do the same thing. Let's say 1.4, 1.5, 1.9, 2.0, 2.1, all the way to 2.4, for example, right? So I have a range of values for W0 and for W1. And what I want to generate is all the combinations of these values, right? That is exactly what mesh grid does. So if I say np dot mesh grid, right? It's not explicit, but what you get is 2.5, 1.4, 2.5, 1.5, 2.5, 1.6, all the way to 2.5, 2.4. Then 2.6, 1.4, 1.5, 1.6, 2.1, 2.4. Then 2.7 in each one of them. So I can generate every combination of W0 and W1 that I'm interested in. Is this fine?
Can you
Yes.
repeat once again?
Yeah. So I start out with saying what are the values of W naught that I'm interested in, right? And they could be like I've listed out here. I know the optimum is at 3. So I'm just going to take a few numbers before it and a few numbers after it. So I can say 2.5, 2.6, 3, 3.1, 3.2, all the way to 3.5, right? Similarly, I can say I want to generate all values, all possible values of W1, and W1 is centered around 1.9. So I'll go from um, uh, 1.4, 1.5, 1.9, all the way to 2.4, right? So these are in individual arrays. What I want is all their combinations. So I want the combination of, I should have written this upper. 2.5, 2.6, 3, 3.5, right? So what I want is 2.5, 1.4, 2.6, 1.4, 3, 1.4, 3.5, 1.4, then 2.5, 1.5, 2.6, 1.5, and so on. So I want combinations, all possible combinations of the W1 and W2. Sorry, W0 and W1.
Okay.
Okay.
The first value with all the first value from W0 with W1.
Yes. Then the
And
next
same,
value
yeah.
is, yeah, right?
Okay.
So effectively, logically, this is the same as for I and W0 range and for J and W1 range,
Yeah,
right?
the
If I look at I
conversion
comma
of
J,
this for loop, yeah.
yeah, right? But the thing is, this gives it to me in one shot, like just one function call, right? And I generate these pairs. Now, if I had just one value of X and Y, right? I could very easily do the calculation of uh, W0 plus W1x for each of these points and calculate the loss at every point, right? But the loss is kind of meaningless because I have just one point. But even then, I can calculate it. I can calculate the error for each point. But I don't have 1 point, I have 100 points. So I want to calculate that error for all of those 100 points. And then I want to I want to square them, I want to sum them and take their average. Hello, Lakshat?
Yeah.
How do I do that? So the first step was mesh grid. The second step was to do the, one second, I just need to plug in. Okay. The first step was to do the mesh grid. The second step is to do um, uh, the actual calculation itself, the broadcasting, right? And in order to do that, so I think I have an example out here. Okay. Okay, how much detail do you want to go into? Let me ask that question. And I'm fine. I actually want to go into the detail, but I want to make sure you guys follow as well. So this is going to go into the details of Python and NumPy. Is that fine with everyone?
Yep.
Okay. So what happens is when I do the mesh grid, right? And I'll show you this in code as well. It actually, it doesn't give me tuples of pairs. It gives me two lists. So this, the first one, so I start with on one axis 2, 3, 4, 5, 6, on the other one -4 to -1. I don't know why I took these values. It doesn't really matter. When I do the mesh grid, I get this 2, 3, 4, 5, 6 repeated 4 times. And I get -1, -2, -3, -4 repeated 5 times. So it matches the dimensions of both the arrays. Okay. And the way I use this is now I do a resize. So I change this 4 by 5 into 451 and 4 by 5 into 451. Okay. So visually it will look like this. So this 2, 3, 4, 5, 6 becomes this 2, 3, 4, 5, 6, each in their individual array and that in a separate array. And then that gets repeated 4 times. The -1 on the other hand will become this. So -1 repeated 5 times, and then that whole thing repeated 4 times. Right? So -1, -2, -3, -4. So now if you look, I have exactly what I was talking about before. If I pair them up, 2 -1, 3 -1, 4 -1, 5 -1, 6 -1, then 2 -2, 3 -2, all the way to 6 -2, and so on. Do you see the structure of what we've gotten?
It's a 3D array, right?
It's a 3D array.
Yeah.
We've done the resize. And now, not just enough to do the broadcast, I have to reshape it. Because now, if I say, hey, look at my X, right? This is, I've got 100 values of X and 100 values of Y, right? So that 100 is, you can think of it as 1 by 1 by 100. And my B0 and B1 in this example are 4 by 5 by 1, right? I talked about broadcasting when we were talking about Python. Do you remember the 2 rules of broadcasting? So one is the number of dimensions have to match. And the second is the shape has to match. Right? So the number of dimensions here is 3. The number of dimensions here is 3, but the number of dimensions here is 1. So if you follow rule 1, I've got to extend it to 3. So I get a 1 by 1 by 100. Is this fine?
Yes.
Yes.
Okay. And now I can say, okay, if I take an array of size 451 and I multiply it by 1 by 1 100. So sure, the number of dimensions match. The shape doesn't match. So for example, this one doesn't match with this 100. So what do? We take this guy and we replicate it 100 times, right? So this will now become 4, 500. And now this 100, these guys match. So I can actually do this calculation for the first column. But now the 5 doesn't match. But that's okay because I can take this 100, replicate it 5 times. And then I can take this 1 and replicate it 4 times. That is what broadcasting is doing for us. And you might say, okay, what is the big deal? The big deal is now in one line, I can say B0 into B1x, and it's going to do this calculation. It's going to calculate y hat for all possible values of B0 and B1 for every data point that I have, for those 100 data points that I have. Hello, Lakshat? Yes, no, or should I go into details? Okay, Amol says okay. What about the rest of y'all?
Yes.
Okay. And then we are pretty much home free because my y hat is now going to have dimensions 4 by 500 and my y is it's 100, but then again broadcasting rules 1 100 and then 4 500, right? So now I can subtract y minus y hat. So what I'm doing is I'm calculating the individual errors, the predicted value and the actual value. I can square them, that's easy enough. And then I add them up along this axis equal to 2. And what I'll get is the loss, which is a 4 by 5 array for every point of the W0 and W1. Right? So instead of writing a doubly nested for loop and doing all of these calculations, my code becomes elegantly simple and at the same time, it becomes very, very efficient. Here. Okay, so I'll show you what I've done out here. So I've done this multiple times to help you understand what is going on. So just take a just go through this to understand what is happening. Okay. So yeah. So I've taken 2.5 to 3.5 and I've divided that range into 100 points. And similarly, 0.7 to 1.7, I've divided that into 100 points. And then I'm doing the mesh grid of the two of them. Right? So I get B0V and B1V. So these are going to be 100 by 100 by 100. Sorry, 100 by 100 arrays. Right? Then this is just explanation, as is this. Okay. Then I reshape that 100 by 100 to 100, 101, both B0 and B1. I don't need to do this, but I still go ahead and say change X to 1, 100 just to illustrate what's happening. And then all I have to do is B0 VR, so that's the vectorized and then reshaped, plus B1 VR into XR. And then Y minus Y hat, this was Y hat, right? Uska square. And then I take the sum along axis equal to 2 and I divide by n. That's going to be my errors or my loss function. Right? So this is the beauty of mesh grid plus broadcasting. Right? Even though it's spread out, it's essentially I take a range of values and I do the mesh grid. And then I reshape them. And then I do B0 plus B1 into X. And np dot mean, np dot square, y minus y hat. Okay. The outcome of this is, I'll come back to the contour, is this plot. When I plot it, so I have my B0 and B1 along these. My loss is along the y axis or the z axis. And when I plot it, you see this curved thing, right? This is something that I really want you to internalize. Yeah, Pritesh.
So even if the shape is same for B0 and B1, we have to reshape it?
Okay, so the shape is the same. We are reshaping it because we want to multiply it with X.
Okay.
Right? So B0 and B1 are 100 by 100. Sorry, out here. Right? B0 and B1 are 100 by 100. X is also 100, but that 100 is different from this. So that's why I took 4 and 5 in our example when I wrote on my notebook. Right? Because what you want is so if I take this 100 by 100, it would work okay if I had just 1 point for X, right? Then I could very easily say, B0 plus B1 into X. That would work fine. I would calculate the Y, right?
Okay.
But I don't have 1 point for X. I have 100 points for X, right?
Okay, yes.
And therefore I need to reshape. So that's why I explicitly reshaped X to 100, just to highlight that fact. Okay?
Yeah, got it. Yeah.
Okay. So do you understand this picture? Right? So even though my f of x is a linear function, the loss function, because I'm taking MSE and it has two parameters, the loss function as a function of W0 and W1 is, I have to use 3 dimensions to plot it. That's point one. The second thing is the reason it's a curve is because I'm taking the square. Mean squared error. If I was doing something else, I wouldn't get a curve. I would get a different shape. Okay? Yeah, Amol.
Yeah, so this point is denoting the lowest error, right?
Yes, the red circle. Yes.
Yeah, out of those 100 error points.
Out of those 100 by 100 possible points.
Yeah, right.
Right?
Yeah.
And remember, I want to highlight this, right? If I pick one particular value of B0 and B1, right? For that value of B0 and B1, we are calculating the loss, which is 1 upon n summation of y hat minus B0 minus B1x whole squared. So it is over all the 100 points. That is one value out here. The next value of B0 and V1, again, we're calculating the loss over all the 100 XY values that we have. And its mean is telling us what the error is. Okay?
Okay. So based on this error, now we are going to predict the value.
Yeah, no, so the idea out here is, see, we already have a closed form solution for W0 and W1. Okay? That part is done. So given a data set, we calculate W0, W1, and then we can easily predict, like if you give me a new value of X, I'll plug that into my equation, W0 plus W1X, and I'll tell you what the Y is.
So you mean, so based on the new value, we are again want to calculate this
No, no, no,
MST.
no, no. No, hang on. Sorry. Stop. Share.
I mean, where we're going to use this MSE?
Yeah. No, so the plot that I'm showing is we want to dive deeper into that loss function. Okay, which is why I do that plot. Yeah, this is what I'm talking about, right? Once I use the loss function, I minimize the loss function, I calculate the W0 and W1 from the training data. Okay, that is my training done. The parameters that I've extracted are W0 and W1. When I go to the testing, then I'm in this regime, right? And I say that, oh, if you give me a point, I can predict what the Y value is going to be. You give me a X, I'm going to predict what Y is. You give me another X, I'll tell you what the Y is. That is my, that is in deployment. Okay. So do you get that? So in the first case, it's a function of W. In the second case, it's a function of the input. The W is fixed. We are not touching W on the right-hand side. Okay. Now, what we want to do is dive deeper into understanding this loss function. We've done all of the algebra. We've taken the derivatives, we've modified, we've rearranged all the terms to get closed form equations for W0 and W1. But in order to go from simple linear regression to more complex models, we need to get a better handle on the loss function. So that is why we plotted the stuff that you saw just now. I'll go back there. This is in order to understand the loss function better. Okay. So it's separate from actually giving it a test point and evaluating what the output is. That is happening separately. Okay. Thumbs up, thumbs down. Okay. The same thing I can visualize as a contour plot. So if I look at this downwards, right, it looks like this. So this is my B0 and B1. And you can see, this, these are the lines where the loss is 0, 0.08, 0.16, 24, and so on. Okay, so it's a different way of looking at it. And if you look at the numbers, so this 0.32 should be out here, but the difference in each line is about, not about, it's 0.08, right? So from here to here, it drops or it increases by 0.08, then again 0.08, then again 0.08. So you can see this side is slightly steeper, if you can use that terminology, than the gap down out here. Make sense? Okay.
Yes.
So I will upload this notebook. I need to clean up some stuff. Go through it very carefully. The first part is very easy, right? Where we're just generating the data, we plug in the equation and we calculate the W0, the B1 and B0. So this is dead simple, but even out here, play around with adding extra points like outliers and seeing how well it works. Okay. The more interesting part is what comes later on. The stuff with mesh grid and with broadcasting. I strongly urge you to get a good handle on it. Again, this is modulo you wanting to use Python or program in Python. If you're okay just looking at the output, that's fine as well. If you don't look at the code, that's perfectly fine, but make sure you understand these plots, right? Because what's going to happen is for linear regression, we'll see how the calculation is very straightforward. We are calculating the mean, we are doing a few summations and a division. So it's very easy to calculate W0 and W1. But this was for a specific linear model. When we go to a point where we are going to have more complex models, we are not going to be hand calculating the derivatives and then plugging in the formula. We want to come up with a more generic way. And this picture is going to help us develop the intuition behind the generic way. Is that fine? Right? Yep. And if you see, there's different, like I can visualize it kind of differently. I can look at different angles. So the code is there if you want to experiment with this. But again, the key point is to keep in mind that I have these parameters, I have a loss function, and it looks something like this. And what I want to find is this minimum value of the loss function. And the question is, how do I do that using a computer? What is an algorithm that will figure out what that loss function is? Okay, and that is going to lead to the gradient descent algorithm. So the idea is when we calculate derivatives, essentially we are saying, we calculate the derivative, we set it equal to 0. But then we can also say, you know what, maybe this is a better, I like this better. Okay. Suppose I pick a random value of W0 and W1, maybe this point, right? Then I can ask in which direction is this loss function decreasing, right? So I can say, okay, if my, I don't know which one is, this is W0, W1, let's say. If my W0 reduces and my W1 increases, that seems to be the direction in which my loss function is reducing. So now instead of doing this algebra and calculating derivative setting to 0, I can just say, okay, start at some random point on this surface and then say which direction is this function reducing in, and then take a step in that direction. And then at the new point, say, okay, in which direction is it reducing? Take a step in that direction. So I keep following the gradient of the function or the slope of the function towards the minimum point. That is the key algorithm in gradient descent. Okay? And we'll get into, I'll make it more explicit, but I want to make sure you guys understand the fundamental idea. Okay? Any questions on this? Going once, going twice. Okay. So let's see. Okay, we've got about 20 minutes left. So I'm going to pause this discussion because the next part where we look at the regular linear regression and then gradient descent is going to take a bit more time. I'm not going to be able to cover it in 20 minutes. So I have one small thing that I want to discuss that I'll cover very quickly. Okay. And this is, it has to do with regularization. And I think you'll appreciate some of what I'm going to say now based on what we've discussed before. So again, left-hand side, I have some data and I can say, okay, let me try to model it as a linear function, in which case I want to find out what the W0 and W1 is. And now we've seen how to do that. We have a closed form. I can just plug in the values for the X and Y's, calculate W0 and W1, which minimizes the loss function. But then I can say, okay, maybe I can take a quadratic um, equation or a quadratic model or a cubic or a quintic model, or maybe, I have like a whole bunch of points. So maybe I'll take a 7-degree polynomial, right? And then the question is, what are the values of W0, W1, W2 that will give me the minimum loss, right? And out here, if I have a 7-degree polynomial that goes up and down like this, it passes through each and every point. So my loss is going to be 0, because for these yellow points, my y predicted and y actual are exactly equal. So ya minus yp is going to be 0, and my loss is going to be 0. The problem is, if you look at these points, right, these points are sampled from a particular distribution, right? So the points that I expect to get when I'm deploying this model are going to be, somewhere in this, from the same distribution itself. It might be thoda upar niche, but it's roughly going to be in this range. And if you take a linear model, sure, it'll perform pretty well, right? There'll of course be some errors, but it'll give you reasonably good predictions. But if I look at this model and I say, hey, here's my test point, the actual value is here, but the predicted value is way off, right? And this is a phenomena that is called overfitting. So overfitting we've come up with a model that is so it's literally memorized the values, the output values for the inputs, and that's all that it can do, right? In general, so you want to avoid situations like this. One thing that we can observe is when you have overfitting, the values of W0, W2 to W7, which we calculate, and you'll see how to calculate for a 7-degree polynomial, these guys. But the values that we use for these tend up being very high, right? So one way of ameliorating this is to say, look, how do I make sure that I do not get large values of W? Right? This goes back to the trick that we used with the slack variables in SVM. Right out there, we wanted to maximize the minimum margin, and then we added plus to that objective function. We added plus c times the sum of the slack variables. Sorry, we changed the maximization into a minimization problem, and then we added the slack variables. The idea being, because it is the objective function is still a minimization problem, it will push the values of the slack variables as low as possible, right? We'll do the same thing out here. So I have my loss function as before, right? And then I'm going to add lambda upon 2 into w squared. W squared माने क्या? W0 squared plus W1 squared plus W2 squared all the way to W7 squared, right? So now this becomes my new objective function, which we'll see how to solve for. But what is lambda going to be? It's going to be a hyperparameter that we've got to figure out, and that is going to tell us how to balance between the original loss function and the value of the W's. So if I take lambda to be, you remember the discussion around W0 plus W1 x1 plus W2 x2, and the value of W's was telling us how important x1 was with respect to x2. It's similar out here. The value of lambda will tell us how much importance we want to give to minimizing W versus minimizing the mean squared error, right? So yeah, okay, I think I've captured all of this. Okay, so this is something called a lasso regression, and okay. The reason why we use lambda upon 2 is because it makes the maths easier. You can imagine when I take the derivative of this, W squared, the derivative will be 2 times W, the 2 will cancel. So it's simply to make our lives easier. There's no other reason. Lambda is a parameter, it's a hyperparameter. We experiment to figure out what it is. There are another 2 kinds of regressions that we'll see. Sorry, not regression, regularization. So this is called lasso regression. The other is ridge regression, where instead of taking the squared of the W's, I just take the absolute value of the W. Right? So this is called ridge regression. It actually stands for something which I never remember. So by using techniques like this, so you should, the overall technique is called regularization, right? And what you should keep in mind is using regularization, you can control how large your parameters are becoming. And the way we do that is to add an extra term to my objective function. Okay? That reminded me, there was one more very important point that I wanted to make. We did this in perceptron and SVM as well, and we're doing it in linear regression, where we're saying that, okay, I want a good solution, right? I don't know how to calculate a good solution, so I formulate it in some way. For SVM, we formulated it as a quadratic optimization problem. Out here, we defined this loss function LMSE, and then we manipulated it. So we've converted the problem of predicting a value or predicting a class in a way that is good, quote unquote good, into a mathematical formula, which we then manipulate in order to get the solution that we want, right? And this is something that you'll see throughout not just machine learning, but in pretty much every field that you have, right? We have a certain objective. We want to figure out some value. And the way to do that is to model it using some mathematical formula and then manipulate that formula so that the solution that we get from the math matches the original goal that we wanted to solve. Okay. Okay, so let me pause out here. Do you have a fair idea of regularization and what it's doing and how it's doing it?
Yeah, one question here.
Yeah.
Yeah, so in this example, in the 7-degree polynomial,
Yeah.
so we say that it is overfitted solution, right? Because the MSA will be 0.
Yeah.
But if you change degree, let's say 5,
Yes.
then would that change the error also?
Possibly, right? It could change the error, and maybe it does better with the test case than the 7-degree polynomial does. Absolutely. And we are going to quantify this as we go ahead, right? I like what exactly overfitting means. You remember I talked about training error and testing error, right? So out here, you could imagine, suppose I plot a graph that looks like this. So I have some data and I'm calculating the MSE as my, sorry. So on my x-axis, I'm putting the degree of my model. And on my y-axis, I'm putting the MSE. Right? So now what's going to happen is, in the example that I had, it seems like the linear model is the best one. So I'll have some low MSE, but as I increase the degree of my polynomial, most likely the error will start going up. Maybe it behaves like that. The training error, right? Well, it goes up, but then when I come to something like 7, all of a sudden we'll find it, hey, for 7, it's actually going down all the way to 0. Right? Or maybe, for all of them, it goes down gradually. I don't know. I mean, it depends on the data that we have. Right? So this is the training error. And if you keep making more and more complex models, you will definitely get lower and lower training error. What do I mean by training error? It's for the training data, what is the MSE? But now if I take my testing data, my test set, and I apply it to this model, what I'll find is that for a linear polynomial, I get roughly the same error. But as I increase the degree of the polynomial, my error keeps going up. Right? This is my testing error. So the definition of overfitting is not that I have zero, uh, uh, what do you call it? Zero training error, because I can have zero training error even with a lower degree polynomial, right? Which is not overfitted. But it is that as I'm increasing my degree, as I'm increasing my model complexity, my training error is going down, but my testing error is getting worse and worse. That is the core meaning of overfitting.
Then is it fair to say the linear equation is more suitable to the solution, or it's all depends?
For this model, yes. Sorry, not for this model. For this training data, yes. Right. But I can, so for example, if my data looks like this, right? A linear model will do pretty badly.
Yeah, right.
Right.
There is
But
a
if
curve
I
here.
take, if I take a more complex model, something like that, right? This could actually do much better.
Yes.
Right? So it depends on the data. The data decides what model is best, and we're going to see how to figure out. But how to decide which model is good is from a combination of the training error and the testing. We won't be using testing error, of course, but validation error. But we'll be using that to say, okay, which model should I be using? Which model fits the data the best? And what you want to avoid is, something like that. Right? And
Yeah.
of course, you see, we are using these pictures to understand what is happening. But when your algorithm is running, it's not looking at a picture. It has to extract properties of the model with respect to the data to figure out whether it is going into a region where overfitting is happening or not.
Yeah. So my next question on the same thing. Let's say in the training, we got that linear equation or the linear
Yeah.
loss function is the best fit for our model.
Yeah.
But in the production data, that error is increased. Then we'll again have to, retrain the model and
No,
maybe
hang
come up
on, hang
with
on.
the.
Yeah. So what happens is the following, and I'll give you a very specific example of this, right? The assumption out here, right, is that so these data points that you see on the top left, right, they are sampled from a certain distribution, right? And the assumption is that in production, when you deploy the model, the distribution does not change. So the points that you get are going to be from the same distribution. Okay. So that is a very strong assumption that we are making out here. So that
But
is
by
not.
but by the time we took a data and new data points come up, those were not
Things
part
could
of the
change.
training. Yeah.
Yeah. No, so that's the other thing that I was going to say. And this happened with us as well. So we had these machines, we had a whole bunch of data that we were measuring. And we were using that to specify what is the quote unquote normal mode of operation of a particular machine. Right. The problem is when you restart the machine, right, that normal mode changes. Let's say you do some maintenance, you tighten a few screws here, a couple of bolts out there, and then suddenly something is not vibrating as much as it was. Right. So the normal mode of the machine has changed. So you need to be able to adapt to that. So now you have to decide whether you want to do what is, and we've talked about this before, if you want to have an online model where you're constantly getting in new data and you're retraining the model or updating the model. But then how do you identify, like if something has gone completely out of whack and you're getting that new data, how did you identify that, hey, this is an anomaly versus this is a data point that needs to be integrated into the model? How do you decide that? You see the difference between the two cases, right? You're getting some new data and you're making a prediction and it's completely maybe not completely wrong, but the error is pretty high on that. First of all, you don't know because it's in production. But
Yeah.
if you get some outlier, so let's say my data is here and my new data point for this value of X, the Y value is somewhere out here, right? So this should either ring an alarm bell or it should be no. The mode, the underlying model from which I'm sampling the data has changed, and therefore I need to update my model itself, right? And that becomes a very subjective thing. So I'll give you an example. So suppose I'm modeling climate change, right? Over a period of decades and centuries, the normal values of, let's say, rainfall in the Indian subcontinent or temperature in Antarctica is slowly drifting, right? So that slow drift means that I want to capture the fact that it is drifting slowly. But all of a sudden, if the temperature in Antarctica has jumped up by 2 degrees, right? I need to flag that as an anomaly, right? So there are some things that I want to incorporate into my model. There are other things where I want to flag and say, hey, this is an outlier. There's a problem out here. And it could be because, we've gone into a catastrophic meltdown or because the temperature sensor got out of whack. Right? And how we deal with it is very dependent on that particular scenario, on what makes sense in that context. Right? So the answer is, I know we've talked about this before. It may be the case that you want to incorporate the data and retrain your model, but that's not always the case. You don't want to do that all the time. Right? Does it answer your question?
Yes, yes.
Right? There's no a golden rule that we can apply. It just depends on the context and of what we're doing.
Yeah.
Okay. Any other questions, comments?
So yesterday we saw the three things: the polynomial, exponential logarithm, and the trigonometric functions.
Yeah.
So far we have touched upon the polynomial and this. I think only one, right? Polynomial.
Yeah, and even in polynomial, we've only touched upon linear regression.
Linear regression.
Function.
Yeah.
Yeah. But don't worry, we are not going to repeat this for all kinds of functions. This was more so that you understand how the math behind it works. Right?
Okay.
And then once we go to gradient descent, you'll see that it actually doesn't matter. We'll figure out the right values, or we'll use gradient descent to figure out the right values. Okay, but we'll get there. Halu.
Yes.
Okay. Any other questions? Sandesh says all good. Right. I know you guys talk a lot, which is great. I want you to continue doing that. Keep having those discussions and articulate what it is that, in your own words, what you've understood and how you've processed all of the stuff we've talked about. We've gone over quite a lot of math, but look at the big picture, make sure you get the core ideas, and you should be good. Right? And the biggest idea out here is I am looking at what my overall objective is. I'm encoding that as a mathematical function, and I'm trying to, and specifically in terms of the loss, and I'm trying to find the minimum loss. And the way I do that is by calculating derivatives and setting them to 0. That's step 1. In step 2, we won't even be doing that, right? But take that key concept, and then you can, anytime you hear about people training their model, even all the way to ChatGPT. Essentially, what they're doing is you have an expected output, you look at the actual output, you look at the difference, and you say, okay, how do I tweak the parameters of my model so that that difference between the actual and expected is minimized? If you understand that, you've understood most of machine learning. Everything after that is just the details of the specific models and how we actually make those changes. Okay?
So that's what differentiate the models, right? The ChatGPT one, the different models.
The models are different, yes.
Yeah.
Right? And it's not simply, oh, this is an exponential function versus a linear function. It gets a lot more complicated than that. But the models are different, their parameters are different, and the gradient descent algorithm is going to tell us how we tweak the parameters in order to, make those adjustments. But essentially, that's what we're doing. We're trying to nudge the calculated value towards the expected value.
Yeah, because right now in our day-to-day activity, we use for our development the Claude and the GPT 4.1.
Yes.
So Claude does a very good job
Mhm.
while giving the answers to our technical.
Yeah.
Similarly, GPT gave it, but it's more general solution. It's not that much technical that we wanted.
Right.
So this makes, I mean, that you said the parameters and the algorithm
Yeah.
that they have used. So this is the differentiator, right, between them.
Yeah. So very specifically, that would be kind of like a hyperparameter, right? To say that, okay, go for a more, what do you call it? Technical answer.
Yeah.
So it would be tweaking it in that direction.
Right.
Right? Or even if you look at Grok, right? That's deployed on Twitter. They are trying to give it a lot of personality, right? So there are examples where Grok says, you're a very low IQ individual. It's while speaking to the user, right? And stuff like that. So it's basically tweaking the hyperparameters to push it in a certain direction, right? And there's a lot you can actually control, uh, like after training as well. So, for example, standard prompt engineering stuff, like if you ask it a question, it'll give you an answer. But if you say that, look, for this particular conversation, here is a sample question and an answer, right? So if you there's it's called something, I've forgotten what it is, but if you seed it with examples, it will do a much better job of giving you the answers. So I saw this very nicely. If you let's say you tell it to write an article on support vector machines, right? It will generate a bunch of stuff. But if you have already written at least an outline and describe different sections, and then you give that to ChatGPT, the output will be 10 times better than just asking it for stuff, right? Or even if you say, give it a document, if you say make it better, it'll fix grammatical and punctuation marks. But if you say, develop the intuitive argument a lot more, or make sure or flag the areas that are difficult to understand and explain those so that the person understands them better. The more specific you do, the better it becomes. So you are pushing it in a certain direction, right?
Is it what is context engineering?
Prompt engineering पता है? Is that what you mean? Prompt engineering?
No, no, the thing that you said, right? You give an
Oh,
example. You
yeah, you
said
give it examples. It might be. I've forgotten what it's called. It might be context engineering.
okay.
Yeah, but I'm not sure. Yeah. ठीक है?
Yes.
Okay, cool. So guys, let's pause out here. Okay, I meant to ask this yesterday and then beginning of today as well. Let's not meet in the next week because I looked at the dates and I'm reaching Arizona on Friday, I think, and I'm very sure I'm going to be jet lagged and my internet may not be up and running. So instead of trying to meet, let's just not meet. But I wanted to ask, are you guys okay meeting tomorrow on Sunday, or do you want to just meet after 2 weeks?
Actually, I'm okay not meeting next because I am traveling also, so
Oh, okay.
I won't be able to join.
Okay.
So
Same.
for me, yeah.
Traveling.
Okay. Pritesh, what were you saying?
I'm also traveling tomorrow, so
Oh, okay. Okay. So then, TK, then let's just not try for tomorrow. Let's just meet. So we don't meet the coming Friday and Saturday. We meet the following weekend.
Yeah, and also we'll get more time to just revised.
digest all of
Yeah,
this stuff.
yeah.
Perfect. Yeah.
I think it will take 2 weeks at least.
Yes, yes.
Yeah, I'll
To
look at
revise a lot
the.
of maths.
It's a lot of math, but like I said, focus on the intuition.
Right.
Don't worry about the algebra and stuff like that. That's not important. It's not as important as the actual intuition behind what we're doing. Okay. And I think I've uploaded yesterday's material. I haven't uploaded today's material. I'll do it in the next couple of days. Okay. Okay, well, guys, have a good couple of weeks, and I will see you uh, whenever it is, 15th Independence Day के आसपास.
Yep.
ठीक है?
Yes.
Okay, and maybe that time we can have a couple of extra sessions to catch up for the missed time. All right?
Yep.
Yep.
Okay. Thanks, guys.
you.
Talk to you later.
Yeah.
Yeah.
Thank you.
Thank you.
Bye.
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 Bye-bye.